I think our project started out by asking questions and defining problems. For me, I was inspired by the predictions of models and theories from previous investigations. For example, at the beginning, I researched about how copper is a good conductor and how the difference in pressure can have a cooling effect. In this picture, you can see my research on heat conductivity. By boiling water in a copper tube and then immediately sealing the tube's ends and then waiting for the water to cool down causes a drop in pressure. Once one end of the tube is heated up, the difference in pressure drives the water vapor to the coolest side, which then cools that area down. So basically, it continually takes heat from one end of the tube and pushes it to the other end. Through my research of air pressure and copper's conductivity and merging my research and ideas with my group members, we were able to ideate and learn how a final product works using similar principles of air pressure, like Gay-Lussac's law and the copper tape. However, this initial phase was really only the exploration and discovery part of how science works, with finding inspiration, making observations, and asking questions. However, when I moved on to sharing my ideas, incorporating feedback and peer review, and discussing with my group members, that's when major breakthrough happens and where we came up with new questions and ideas. For example, we combined many other ideas like the application of conduction and convection of heat. I learned how collaborating creates a synergetic effect, and it goes to show how examining models and theories leads to me seeking additional information, and how that information sparks more ideas. Bouncing off my ideas with my group members and them with me allows us to engineer something through the culmination of our thinking, and this exemplifies the quote, "The whole is greater than the sum of the parts." Additionally, working in a group allows me to address scientific questions and solve problems, and communicate technical information and ideas. I respectfully and thoughtfully provided critiques on arguments and challenged ideas and conclusions. A simple example of this is that one of my group members thought we should conduct our experiment outside on a terrace, for example, to simulate real-world environments, concluding that that is what we are striving for, to show our product working in the real world. However, I explained that this introduces a myriad of confounding variables, for example, major temperature and humidity fluctuations, wind, rain, etc., that can change from day to day or even in a couple of hours. If we went ahead with this, the perceived correlation between percentage filled with water and the difference in temperature in a model would not be accurate, if there even was a correlation at all. I made and defended a claim based on evidence about a natural world, taking into account possible unanticipated effects on the performance of our proposed system. Some contributions I made to the group were documenting the project process, supplying the water bottles we used, and putting copper tape around the smaller bottles. To make sure that air was flowing into the box only through the water bottles, Shipper and I sealed off any gaps in the box. Our independent variable is the percentage of water filled in the bottles. So if air flows into the box from somewhere else, the heat won't be dissipated into the water, and there won't be an accurate correlation between the independent and dependent variables. I also helped calculate the box dimensions and construct the box. While doing so, the box was created as small as possible. This is starkly different of what the other group did. Doing so ensures that this design solution is more efficient. It makes sure that there is less volume of air to cool. If the box was bigger, we might have to wait for more time for a noticeable difference or change in temperature each time we conduct our experimental trials. Our major problem was water leakage. What we actually observed was very different from what we expected. I learned that trial and error is an important part of this process. I need to learn what went wrong, why and how it went wrong, and what I can learn from it and what we should do next. Over time, we revised our model and negated this problem by using hot glue and parafilm. This reduced the water leakage, however, it did not stop it entirely. Therefore, our first round of experiments were vastly different from what we expected. Since I'm conducting my experiment in a relatively controlled environment in my elevator, I can't let the water leak onto the floor. I wanted to put it inside a bucket, for instance, to collect the water. However, this introduces another problem due to fluid mechanics and how air flows. There would be less airflow going into the bucket and then into the water bottles. So I used two buckets, with one of them being upside down, to make sure that air can flow in freely while allowing water to be collected. At the end of each trial, the water level has gone down to 25%, which was where the lowest hole was. If there was a hole in the water bottle lower than that, all of the water would have leaked. At the end of the experiment, there was little change in temperature and our independent variable had no effect, since for all of the trials, 0%, 50% and 100% water filled, the average change in temperature were all around 0.4. Something I had just thought of was using a silicone gun. This is a special cartridge filled with silicone to seal up cracks or gaps. Many people use this in their households for bathroom tiles, for instance. After doing this, there wasn't a drop of water leakage. And in our second round of experiments, there was actually some correlation we could see between our independent variable and our dependent variable. However, it wasn't all smooth sailing. For the experiments I conducted, just like developing our eco-cooler design, the theory part of it and learning how to use the instruments and the data collection methodology was the easy part, but the practical part was much more challenging. Instruments randomly disconnected from time to time, resulting in me having to rerun a lot of the trials. Additionally, the elevator doors, for some reason, blocked the connection between the sensors inside and my computer outside, so I had to put my laptop along in the elevator, so I couldn't really monitor the progress of the experiment until each trial was over. Additionally, making sure which temperature probes I labeled inside temperature and outside temperature is something I triple checked. At the end of our second round of experiments, I exported the new 9 trials to my Google Drive, and then compiled the new data into one master document. Through constant revision, never-ending learning, and regular reflection, I'm able to improve and learn from mistakes. In fact, here's what I said in one of my reflections. Learn what to keep on doing as a group, as to how we work together, if it's good or not, and what to change for the next time we work together. Looking forward, I want to keep these structures of teamwork, reflection, never-ending learning, and constant revision for future projects.